All right, so finally, we've reached the last section of the semester. It's about area within a polar curve, and we need to develop it. One last formula. Just give me the formula. No, no, no. We got to develop it. So consider when you're doing this, there's going to be kind of a parallel to what we did with rectangular coordinates, where you're integrating, say, from A to B, and my Calc 1 students are all puzzling over area under a curve and things like that. And of course, what you do and what you did in Calc 1 was you just broke this up into, subinterval pieces, and you used a rectangle, a Riemann sum using rectangles, and you added them up and said, well, the area under the curve is approximately this. We do the same thing with polar. Okay, so you have some sort of function. R is a function of theta. Okay, if that's a theta. And you have limits for theta. Let's say it goes from, I don't know, alpha, which is angle alpha right there. We don't care about the arc right now. And then maybe cruising on over to some other angle, beta. And this curve is doing whatever it's doing, okay? So from here, who knows what it's doing? It could be a cardioid. It could be a rose, part of a rose curve, things like that. Okay. And let's look at it this way. We take the theta interval from alpha to beta, and we still do the slicey-dicey. But when you fan it out, literally, I'm going to think about a fan that you fan out. You have these little angles, these delta thetas, if you will, marking out the area. Okay, so if we take a look at one of them, maybe the second one there, you got rectangles on this side. You got, what do you want to call these things growing out on this side? Maybe I cut it off here and think of it as a sector, or these are sectors of a circle. You know what? They're not exactly that, are they? Well, neither is these little widgies underneath this curve on the right-hand side. Are they exactly rectangular? It's a nice smooth curve, just like R is. So we have to go back to geometry and talk about area of a sector to approximate this. So the area of a sector, okay, from geometry and also from trig, is the following. You take the area of the circle, pi r squared, and you hit it with a fraction. And the fraction is your angle, theta, in radians, divided by the entire circle angle, which is 2 pi. So that's how it works in geometry. And of course, we cancel the pi's, and we get a formula that says the area is 1/2, right? Theta r squared. Okay. And we're going to use it, say, on every one of these little sectors. So in this picture, we're going to sum up all of those a sub i's, and it's going to approximate, like I equals 1 to n. It's going to approximate the actual area. So we got to look at each one of those a sub I. So a sub I is really, it's looking like this. All right. And we have a circle, let's say. The angle here, if we use each one of those is of the same width, the angle then is, believe it or not, delta theta, because theta is an angle and delta theta is a small little nudge of an angle, a small sliver, let's say. But then we have a circle. If we have the theta already, that's going to be delta theta. That's our angle, okay? But we need the radius. For the radius, we're going to plug into our function, because that's how you find r's. So somewhere in this interval, we're going to pick an r sub I star, and we're going to plug it in. Now the curve itself, wherever it might be, I'm going to have to put another color here, like green or something. The curve could be, you know, whatever it might be doing. I just made it exaggerated. And we're just going to assume it's a perfect circle, just like we assumed these guys were perfect rectangles underneath the curve. We're almost there. Okay, so therefore, this I'll call r sub I star, and it's found by plugging in. It's found by plugging into the function f. What are you plugging in? One of your angles in this interval, in delta, in this interval, whatever interval you're talking about. And so that guy is going to be theta sub I star. Okay, so the radius of the circle is r, but it's found by plugging in theta sub I star into the function. That's how you deal with polar coordinates. That's how it works. You want r, you plug into the function. And so going in for r over here would be f of theta sub I star. Okay, and I'm going to cut to the chase now. You ready? So when you plug these guys in, what you get is you've got a delta, theta, of course, and you got the function, but it's being squared, and then you have this multiplier 1/2. So here we go. The area function is going to be the integral from alpha to beta. You're going to go all the way across, and it's going to be 1/2, and then your function f of theta squared d theta, or you can write it as integral alpha to beta 1/2 r squared d theta if you wish. Okay, and that's it. You know, you have a 1/2, you have a square of your function because of the area of the sector game that we played. There's no other way to do it. You can't do rectangles here. Look at the shape of this thing. That's a sector. Very good. That's the development, and you know, different ways of looking at the formula. Okay, so we cruise down here. I have 2 examples, and I think I'll do this in one video. Here's the first example. It says, find the area contained within the polar curve. Oh, I know what you are. You're a cardioid. Okay. I have to say that when you're doing these problems, you're going to want to maybe sketch a little to see what's going on. Now, if I knew it was a cardioid in my mind, that means a student doesn't know that, and you guys are studying that. And so if you do a little bit of work on it, it's out to 4, it's 2, and 2. Yeah, this guy is cusping to the right. What does that help me do? I don't know. It helps me envision maybe what theta is doing. From the origin outward, we could have the entire area inside this curve with the formula we developed up there. Let's write it down again. A is equal to etc. Okay. Now, if you're looking at that picture while I'm writing that, good. If you're thinking symmetry, awesome. You could use symmetry on this. I'm not going to do it, but I could, okay? Remember the last time we were doing the arc length and it was like, oh my goodness, that was a crazy problem. Well, this time we're doing the area inside this particular guy. So what you could do then is simply do the following. The area in our problem is the integral. If you want the whole thing, you're going to have to spin all the way around, baby, all the way. So it's like a lawn sprinkler that's all the way around. This guy's going to go 360. So my limit should be 0 to 2 pi. Okay. That's the important part of sketching is I get the limits right. Okay, so we're getting 1/2, and then the function here is 2 plus 2 cosine theta squared d theta. Okay, so I'm just going to attack it. I'm going to go, okay, I got 1/2 here, integral 0 to 2 pi, and this is good for you to see me go through this too. 4 plus 8 cosine theta, and then plus 4 cosine squared theta d theta, something like that, okay? If you want, you can factor out the 4 and get it out of the way. I'm going to leave it alone. I'll just simply keep working on it. It's 1/2 integral, so it's almost good to go. We can integrate 4. We can integrate cosine, but what do you do here again with cosine squared? Think about it. It's an identity. It's plus 4 times 1/2, 1 plus cosine 2 theta. That's what we did way back at the beginning of the semester is we used an identity from trig to enable us to integrate. So we got the 1/2 here, and we've got the 4 and the 8, and all I'm doing is cleaning things up. That looks like we've got a, now that's a 2, right? So we have plus 2, and then we have plus 2 cosine 2 theta, d theta. I like to put the numbers together, so 1/2 integral, let's say 6 plus 8 cosine theta plus 2 cosine 2 theta d theta. The only one that's an issue is that last term. We're doing pretty good. We got 1/2, here's the integral, 6 theta. And this is going to be plus 8 sine theta. And then we're going to have, you got to do a little u is equal to 2 theta. You get a 1/2. So you're going to get a plus sine 2 theta. And going from, what, 0 to 2 pi? All right, so let's see what we got. We got 1/2 waiting outside in the wings. Plugging in 2 pi, you got 6 times 2 pi. And I'm going to save us some time. It's going to be plus 8 times sine of 2 pi is 0. Plus sine of 4 pi is 0. And then minus 6 times 0 is 0. And 0 and 0. So the whole thing is 0 right there. And really the only operator is up front here. So our answer is 12 pi, but half of that, so 6 pi is the area within that cardioid. Whoa! Cool stuff. Really good stuff. Yeah, so if you've got one curve, it can be pretty straightforward. And I also wanted to mention this too, by the way, if you thought of this. You could have used, or you can use symmetry. And I would say the area is equal to the integral. Okay, here's the thing. If I sweep out the top, it's identical to the bottom part of the curve. So you can go, why don't I just go twice 0 to pi? And same formula, it'd be 1/2 2 plus 2 cosine theta quantity squared d theta. And work it out. And you'll get the same answer. You will. Okay? So symmetry works, but you have to have it graphed to see it. Okay, let's do another one. This one is more involved. This is our last example. And its area, I think it's going to be a little more involved. Okay, finding areas between curves means you really want to be sketching well. So let's see what's going on here. Find the area that lies lies inside, and I'll write this out. R equals 1 plus cosine theta. And you know the magic here, and it's going to say outside. Okay, so outside, R is 2 minus cosine theta. So R is equal to 2 minus cosine theta. Okay. The magic here is, can you sketch? Because you got to be able to sketch. All right. So it's inside and outside. We got to draw ourselves a pretty good picture of this. Let's see what's going on. Okay, so let's do the first guy in blue. And we'll do this guy. Well, that's a cardioid with a cusp. I'm starting to get better at that. How about you? It's out here at 2, and it hits here at 1. Maybe I should make this a little bigger. Okay, let's do this bigger. Okay. So he's out here at, say, 2, and that guy, yeah, okay. He could be 3. Okay, so well, let's say that this is 2, and then this is 1, and, okay, we've seen this guy before. He's cusping, right? Okay, so that's that guy. Let's do the other guy. Let's do green. Does that show up okay? So green, he's going the other way, because if you plug in 0, you've got 1 here. Okay. If you plug, okay, so that's 1 about there. And if you plug in like pi, okay, no, I'm sorry. If you plug in 0, you're at 1. I'm sorry, I went the wrong direction for some reason. Okay, he's there. But if you plug in pi, you're actually way out at 3 somewhere. Okay, if you plug in pi over 2, you're at 2, aren't you? And this guy's at 1? Yeah, so he's up here and also down here. And this is one of those guys. Is he that big? I guess so. Let's see, did I do this one right? No, I didn't. He should be at 3. So my picture is not great, but I'll fix it. Let's fix this. This guy's at 3 here. And he crosses. No, he's not. Weber, you're crazy. He is at 2. Okay, he's at 2. And that's 1. And it must be the end of the semester. Here we go. And, okay, let's just go around the horn. If, little table here or whatever. If cosine, if theta is 0, you've got a 1. So he's at 1. If theta, okay, he disappears, so he's at 2 now. He's also 2 down here. And if you go to pi, the guy goes to 3. So the curve is, let's see, it's doing some sort of dimply thing, as I recall. And my picture is going to be horrific, but it's doing something like that. So it doesn't have to be perfectly wonderful. Let's do this right now. It says it's inside the blue curve and outside the green curve. It's outside that guy. So let's do a picture of that. Where is that? Okay. Inside blue, outside green. Here it is. Looks like we can use symmetry on this. Let's use symmetry on this too. Okay, so novices, here's what's happening. Is we're going to allow theta to spin outward like this until it reaches this magic point where they run into each other. And also down here. But the thing is that there is an inner and an outer curve. Just like in rectangular coordinates, you have an upper curve and a lower curve, and you're subtracting. You subtract here too, man. Here's this guy, you can barely see him, but that's the bottom curve, if you will, and that belongs to this guy. Remember, the blue curve is this guy. Okay. So our formula does the same thing. You're going to actually compute the area inside the blue curve and then minus the area inside the green. That's how this works. But you watch the limits. So the area would look like it's the integral from, I don't know yet, 1/2 the farther curve squared, and then minus, keep it all in one integral, the closer curve squared d theta. The farther curve is Mr. Blue, and it's 1 plus cosine theta. And the farther curve is Mr. Green, okay? And he is 2 minus cosine theta. This is done, except for the limits. The limits have to be found. And the limits are, what are these angles where they cross each other? And what do we do to find that out? We gotta, where do the curves intersect? There's right here. I can't even read my own writing. That's pretty typical. Intersect. Okay. What do we do? Tried and true method. Set them equal to each other. So 1 plus cosine theta is equal to 2 minus cosine theta. Bring the cosines over. I got 2 cosine theta is equal to 1. So cosine theta, what, is equal to 1/2. Cosine theta is 1/2. You know what that is? Theta is pi over 3. Okay. So this angle is pi over 3 right there. I don't care about what r is. This guy's negative pi over 3. And there's some beautiful symmetry there. You know what I'm going to do is I'm going to just do the top portion. And this is weird. You really have to look at it. You stop right there, because if you go any farther, things get messed up. Suddenly the blue curve is underneath and the green is above. And we don't want that. We just want this sliver in here. Okay. So we're going to double. I'm going to double this myself, and I'm going to go from 0 to pi over 3. Now the rest is integration. I don't know if you want to see me do it. You can pause it and stare at that, and I'll write a little note here also. I'm using symmetry right there with that 2. Okay? That means I'm getting the top part, and I'm doubling to get the bottom part all together. So the rest, I'm going to factor out the 1/2. They're going to cancel with the 2. I'm going to square. And let's see what we've got. We've got 1 plus 2 cosine theta plus cosine squared theta. And then in here we've got minus, I'll use parentheses, 4 minus 2 minus 4 cosine theta. And then we have plus cosine squared theta. I have a feeling that things are looking up. We've got integral 0 to pi over 3. Let's see what we got. This guy ends up being minus 4 plus 4 cosine theta minus cosine squared theta. And what I was looking for was cosine squared minus cosine squared. Yeah, cool. Easier. But we've got this 1 minus 4 is minus 3. That's this guy with that guy. And then we have 2 cosine plus 4 cosine is plus 6 cosine theta d theta. Integrate. So we get, wow, we got that's weird. Okay, we're integrating, so we're going to get minus 3 theta. Ooh. And then we're going to go plus 6 sine theta from 0 to pi over 3. Okay. Let's see what we got. I don't know. I don't feel comfortable about what I got. Something's wrong, but okay. I got right here negative pi. Okay. And then when I plug in pi over 3, I've got plus 6 times O ye of little faith, right? What we have is a radical 3 over 2 for sine. That's 3 radical 3. And then we're going to plug in 0, where you're going to get 0 there. So what we have is 3 radical 3, but minus pi. You know what that minus is? You're losing some of the area of the green guy, of the green curve. That's it. I hope it's right. Pi is, what is it, 3.14? And 320. Okay, there's a positive answer. So that's it, baby. And that's it for this video. Took a little while. That's a good one to stare at and study. All the steps that you have to do in this problem, where you got to graph it, you got to find out where it intersects. I'm using symmetry on that. And staring at that thing, there you go. Okay, you guys, that's it for this one.